Very nice. Okay, so after this part, you would be able to remember the short history of thermodynamics as a branch of science. Okay, we would start with a short history. Then we will understand some terminologies in thermodynamics. This one is also very important because when we learn something, we should be sure that we are speaking the same language. Here, I mean the language of thermodynamics. There are some terms, terminologies that you should know, you should understand before we go further. These are very basic terms when we talk about thermodynamics. Okay, and of course, understand some basic concepts, some basic definitions in thermodynamics. So to be sure that you understand it very well. Okay, then what is thermodynamics? Do you have any idea? Hứa Hải Minh. Hứa Hải Minh. Yes. What is thermodynamics?
I think thermodynamics is about heat, temperature, and energy.
Yes. Okay. In Vietnamese?
In Vietnamese, nhiệt, động lực học.
Very nice. Thank you so much. Thermodynamics. Here, this word is composed of two parts. Okay, the thermal. When you see something that has the thermal, you know that we are talking about heat, something related to heat. And the dynamics is actually the movement. Yeah, the movement of the heat. So here, when we talk about the thermodynamics, we talk about a branch of science which deals with the energy transfer and also its effects on the properties. Here we have physical properties and chemical properties of the substance. So this is the thermodynamics. If you look around you, for example, in the kitchen, you can see that the kitchen appliances are mostly all of them are engineered using the principles of thermodynamics. You can see, for example, the oven, you can see the refrigerator, so you can see even the air conditioner, the furnace. So all of them are engineered using the principles of thermodynamics. Even the thermal power plants, okay? So a lot of things in our modern world are using the principles of thermodynamics. Okay, and for the short history of thermodynamics as a scientific discipline, so we could start with Otto von Guericke. So actually, he's a German scientist. He was the first one who built and designed the first vacuum pump, something related. Yeah, an application of thermodynamics very soon in 1650. And I took a picture of him on the internet here. Later on, you have Robert Boyle. He was actually Anglo-Irish physicist and chemist. So he cooperated with Robert Hooke to build an air pump. So maybe you heard about the Boyle, right? The Boyle law, yeah, the Boyle-Mariota. So he's also very famous. Even Robert Hooke, you should also heard by him. Then a little bit later on 1679, Denis Papin, actually he's a French physicist and mathematician. Denis Papin, Okay, he was the one who built a steam digester. Okay, another application of thermodynamics. And then we have Thomas Savery, an English inventor and engineer who built the first engine. Actually, he was the one who built the first engine, but it was Carnot who was much more famous. Carnot, Sadi Carnot, he's a French engineer. He was named the father of thermodynamics. Further, the father of thermodynamics. Actually, on 1824, he published the reflections on the motive power of fire. This was a discourse on heat, power, energy, and the engine efficiency. We, in this subject, we will also learn about the Carnot cycle and the Carnot engine. So you will discover that no real engine can go over than the Carnot engine efficiency. So he was the one who set the limit for the efficiency of an engine. Very famous one. Trình Carnot, Carnot cycle. Maybe you heard about it, right? Before even we started the thermodynamics. And then later on, we have Willard Gibbs. You should also heard about him, who showed how the thermodynamics processes could be graphically analyzed. Okay. And then in the early of 20th century, we have several names. We have Gilbert Lewis, Mertley, Randall, and so on. They apply the mathematical methods of Gibbs to the analysis of chemical processes. So these are very short histories. So you see several very famous names already that were the first one who built the fundamentals of thermodynamics. Now, as this branch is developing, now we divide the thermodynamics into several branches. We have classical thermodynamics, we have statistical thermodynamics, chemical thermodynamics, and equilibrium thermodynamics. So for the classical thermodynamics, so we described the states of thermodynamic systems at near equilibrium, that is the macroscopic measurable properties. So this branch is used to model exchanges of energy for work and heat based on the thermodynamics law, things that we are going to see in this session. For the statistical thermodynamics, so this branch relates the microscopic properties of individual atoms and molecules to the macroscopic, the bulk properties of material. So thereby explaining the classical thermodynamics as a natural result of statistics, okay? The classical mechanics and quantum theories at the microscopic level. In the next slide, we are going to go deeper into the definition of what is microscopic system, microscopic properties or macroscopic properties. For the chemical thermodynamics, this is actually the study of the interrelation of energy with chemical reactions, with a physical change of state within the confines of the law of thermodynamics. So that's why you see during the second semester when you study the subject called general chemistry 2, you will see a part of the chemistry which is very similar to the thermodynamics one. Okay, very similar. You will see it for the second semester. And finally, the equilibrium thermodynamics. This is actually the study of the transfers of matter and energy in systems or bodies that can be driven from one state of thermodynamics equilibrium to another. So we will discover into a little bit deeper the thermodynamic equilibrium in the next slides. But here, actually, this term indicates a state of balance. Okay. Now we go to the first concept. Very important when we talk about the thermodynamics. We are going to talk about the open system, the closed system, and the isolated system. Okay. Here, the open system. So in an open system, both energy interaction and mass interactions take place. If we look at this picture, do you see the mouse? Các bạn có thấy con chuột không nhỉ?
Yes, we can.
Yes, you can.
Good. So here, this is the example, an example of the open system. I have a pipette. Inside, I have a substance, right? And this pipette is opened. It's opened. So what we see here is that. So the matter. So I mean the mass, the matter here, the mass can be transferred from this pipette to the surrounding. Okay, so we have an interaction, the mass interaction. And the heat can also be transferred between this and the surrounding. Okay. Sorry. Sorry, I have a phone call. So you see here for the first example, when we let the pipette open like this, we have the mass transfer and also we have the heat transfer. We call it an open system. So based on this, I think you can define already what is a closed system and what is an isolated system. So let me try. Nguyễn Mạnh Dương, so what is a closed system? Try it.
I don't know. You can repeat.
You don't know. What I don't understand is that when I see your camera here, but when you talk, I don't see your mouse like moving. What happened with your avatar? Are you using a fake avatar or something?
My internet not working correctly.
No, it's not because your lab. I see you from the beginning. Try to talk, try to say something. Mạnh Dương.
Yeah.
So you see, your mouse is not even moving. Yeah. So don't play trick with me, okay? You have to try this. You change to your real camera, or I kick you out. Nha, các bạn đừng có chơi chiêu với tôi. Đây không phải là lần đầu tiên mà các bạn học đấy. Chứ đừng làm cái trò đấy. Thêm nữa là không ai ngồi học trên giường cả. Một là học hẳn hoi, hai là nghỉ, có thế thôi. Okay, for the closed system, in a closed system, only the energy interactions and no mass interactions take place. Here we go into the second example, the second one. You see, now we have the same pipette, but we close it. But this, actually, this is still movable. But when we close it, there's no mass transfer anymore, no mass transfer. But the heat, yes, the heat is still can be transferred from this to the surrounding, and this system can do work also. For such a system, we call it a closed system. So there's the energy interactions, but no mass interaction. Okay. And for an isolated system, of course, here we have the same pipette, but now it's very well insulated. So no heat transfer takes place, no mass transfers take place. Then we have an isolated system. Okay, please remember very well: open system, closed system, isolated system. We already mentioned about macroscopic and microscopic system and their related properties. So macroscopic system is concerned with the effect of a certain number of matter, and these effects can be perceived by human senses. So when we talk about something that is at the macro scale, we know that we are talking something that is big enough for us to sense, to perceive. For example, here we have the pressure, we have the volume, we have number of moles, so we have the temperature, for example, something that can be perceived by human senses. And of course, associated with a macroscopic system, we have macroscopic properties. Okay, I have already mentioned some: pressure, volume, temperature. We may have also the density, the composition, the viscosity, etc. And for the microscopic system, actually, the microscopic system is concerned with the effects of the action of many molecules, and these effects cannot be perceived by human senses. Yeah, this time, the microscopic. When we talk about a micro, okay, we know that we are talking about something that is very small, and the effects of the system cannot be perceived by human senses. Associated with a microscopic system, we have microscopic properties, right? For example, here we have the molar mass, we have the velocity of atoms or molecules, we have the momentum, we have the kinetic energy, etc. Okay, microscopic and macroscopic system. Then we also have to distinguish the intensive properties and extensive properties. Intensive properties and extensive properties. The intensive properties are also called the intrinsic properties. Here, the intrinsic properties. So these are properties that are independent of the mass of the system. Independent of the mass of the system. For example, we have the boiling point. So do you agree with me that the boiling point is independent of the mass? 1 kilogram of water will boil at 100 degrees Celsius. 1 drop of water will also boil at 100 degrees Celsius, right? We have the color, the temperature, the luster, the hardness. So these are also intensive or intrinsic properties. And in this way, we have extensive properties. Trần Ngọc Phượng. So what can you define for the extensive properties?
Is the property that are independent of the mass?
No, independent of the mass, we have intrinsic properties. Now for the extensive property, so it should be dependent, right, of the mass, independent anymore. Be careful, okay? We have extensive or extrinsic properties. So these properties are dependent of the mass of the system. Dependent. So we have the mass itself, of course. We have the volume, right? We have the weight, we have the size, and so on. These are dependent of the mass, of the substance. Okay. And we will go to 3 more very important basic concepts. I don't understand the question of Mr. Trương Tuấn gì đây? Trương Tuấn Nghĩa. Okay, some material don't have exactly boiling point. How can we describe when they turn into the liquid? What is your question? How can we describe?
I want to know if the question is about some material like plastic. Yeah. So when we it not really have it is melting point, not boiling point. Yeah, I'm sorry.
Actually, it depends on the material. So when we talk about the plastic, for example, there are a lot of thousands kind of plastic. Okay, so it's not pure. So plastic is actually a composition of a lot of hydrocarbon, hydro and carbons. Okay, with different structure. That's why you might see that, okay, we cannot find the exact boiling point because you should know the structure also. But here, for example, we talk about pure elements, aluminum or something like this. It should have an exact boiling point or the exact melting point even. Okay.
Yeah. Okay. I got it.
Now let's continue. What do I stop? Okay, we should define the state. This term is very important when we talk about a thermodynamic system. Okay, so a state is defined. A state of the system, I mean, is defined by specifying the values of a set of measurable properties that are sufficient to determine all other properties. Okay, this is the state. For example, the state of a fluid system requires volume, temperature, pressure. Based on the three properties, volume, pressure, temperature, we can determine all other properties of the fluid. And a process. So any change of the state of the system, we call it a process. And the process path, actually these are infinite states through which the system passes while going from initial state to final state. If you look at the left here on the picture, here this is called a PV diagram, a pressure volume diagram. We have the pressure for the y-axis and the volume for the x-axis. Each dot in this diagram, each dot, okay, represents a state of the system. For example, here we have state 1, we have state 2. When we change from the state 1 to the state 2 like this, okay, state 1 to state 2, actually we have a process. When we change from one state to another, actually we have a process. And the curve that links between the state 1 and state 2, here we call it a process path. Of course, so from 1 to 2, you can have infinite process path. Okay, if we draw something like this, we have another process. So each dot here represents a state. It has a pressure and a volume associated with it. Is it okay? State, process, process path. Now, when we talk about the process in the thermodynamics, we have two more important definitions: the reversible process and the irreversible process. Okay. The reversible process is a process that can be reserved in order to obtain the initial state of a system. So from the initial state, we go to another state, and then you can have a way for the system, for your system to go to the initial state again. So we call it a reversible process. For example, we have a uniform and slow expansion or compression of a fluid in a piston. You have a piston. You expand it or you compress it in a cylinder. Okay, a piston with a cylinder, you compress it or you expand it slowly. So you can always have a way for your system, a piston and cylinder, to go to the initial state of pressure, of temperature, and of volume. So we have a reversible process. And inversely, we have an irreversible process. So a process that cannot be reserved, right, in order to obtain the initial state of a system. Okay. For example, we have the heat transfer. So we know that the heat is transferred from the hotter place to the colder place, right? Hotter place to the colder place. Then, but there's no way that we can reverse the process. Yeah. If heat already transferred, heat is always transferred from the hotter place to the colder place. So there's no way for us, for this process to be reserved. Would you agree with me? The same with diffusion electricity flow through a resistance also. So these are some examples of the irreversible processes. Is it clear? We will continue to the equilibrium, thermodynamic equilibrium that we just mentioned in the first slides. When we talk about the thermodynamic equilibrium, we can distinguish the thermal equilibrium, the mechanical equilibrium, the chemical equilibrium, or the phase equilibrium. So when we say that a system is in the thermodynamic equilibrium, so we mean that there's no tendency for the state of the system to change spontaneously. Okay, no tendency for the state of the system to change spontaneously. For example, the gas in a cylinder with a movable piston. So this system will be at equilibrium if the temperature and the pressure inside are uniform, and if the restraining force on the piston is just sufficient to keep it from moving. So we will have mostly the same temperature, the same pressure, the same volume over time. So we say that the system of the gas in a cylinder is at equilibrium, thermodynamic equilibrium. Now, if we distinguish, we would have the thermal equilibrium, okay? So when we talk about the heat transfer, we will have like, once the heat is transferred from the hotter place to the colder place, and at the moment, we have the same temperature from the two places. So we obtain the thermal equilibrium. Okay? For the mechanical equilibrium also, for example, I have an example here. If this ball stops, doesn't move anymore, doesn't fall anymore, we may have the equilibrium. For the chemical equilibrium, so let's the substance A react with the substance B, and then we have the substance C and substance D. We would have the chemical equilibrium when all the masses, do not change anymore. So we have a stable mass of A, B, C, and D. Then we would have a chemical equilibrium. Okay. And then phase equilibrium. Of course, when there's no change of phase from the solid, liquid, vapor anymore, we would have the phase equilibrium. Okay, this is the first part. I think we could take a break of 10 minutes. Normally we take a break of 10 minutes, right? Okay, so while you return to the class, I will check randomly your attendance once again. Randomly your attendance, especially for people who do not have the camera on. Yeah. So then I will kick them out again and again, and at the end I will have the final list for my attendance checking. Thank you. See you in several minutes.
Okay.
Okay. It is a little bit cold. So now I will try to check randomly. Nguyễn Hoài Anh ngồi đâu mà trông tối thế? I will check. Mai Ân, are you here? Bạn Mai Ân. Temperature. So we know that the temperature is the degree or the intensity of heat present in the substance or object. We talk about the temperature, we talk about the intensity of heat, right? And heat, the temperature is one of the 7 basic SI quantities. Do you know what is SI? Who know what is SI?
International Unit System.
Oh, very nice, International Unit System. Then why not IS? Why SI?
Viết theo tiếng Pháp à?
Yeah.
Spelling.
Yeah, this is in French. Système International. Okay. You are studying in Vietnam, France University, so you will learn French also. Vous allez apprendre le français. Hein? Deuxième année, troisième année. Okay, French. I've been studying in France for 5 years, and then I changed to
Recording stopped.
To Luxembourg and to Belgium for more than 2 more years. And before I go back, I went back to Vietnam. There's a problem with the record, right? I see connecting.
Yes, you stop your recording.
So do I need to restart my record or something? What is the problem here? Này là bị làm sao các bạn nhỉ? Như này là đang record không?
Đang không record thầy ạ.
Đang không record thì ạ.
Không ạ.
Thế thì bây giờ làm sao, bởi vì là tôi cần
Thầy thử ấn bật lại cái record em ạ.
stop xong rồi ấy à, hay như nào? Để tôi xem nhé. Record on the
Control A.
đây đang thử record on the cloud. Is it okay? Because I need this record to send to several students, not, I mean, 100 students who are doing the military training. You will be in the next year, I hope so. I'm not sure if it's already recorded.
It's still not recorded.
Recording in progress.
Oh, no, it's recording.
Nice. We have the record once again. We continue. So the SI quantity, of course, we have we know already several temperature scales that we are using in our world. We have the Kelvins, we have degree Celsius, we have Fahrenheit, degree Fahrenheit. Please take a look here for Kelvins. We do not have the sign, the small sign for the degree, okay? And we also do not say degree Kelvins. We say only Kelvin. For degree Celsius, of course, we have the degree, the small sign, and for the Fahrenheit also. We can convert from one temperature scale to another using this formula. From Kelvin to degree Celsius, from degree Celsius to degree Fahrenheit. Okay, using these formulas. And here I show you some examples of the temperatures. So here is the lowest temperature that we can record, the human can record. Okay, 10 to the power minus 9. Here is the temperature of the surface of the sun, around here. 10 power 4, okay, Kelvin. And here, this is an estimation of the temperature when the universe just after the beginning, very high, very hot. 10 to the power of 39. Now we go to the zeroth law. In the zeroth law, we talk about the thermal equilibrium. So if the bodies A and B are each in thermal equilibrium with the third body T, then A and B are in thermal equilibrium with each other. Nowadays, we see that this is quite obvious, but actually, this law was discovered even after the first law of thermodynamics. That's why it has the name of zeroth law, because people already stated the first law, and then they invented this law, but the number 1 was already taken. Then they had to use the number 0. That's why we call it the zeroth law. Định luật 0 tìm ra sau định luật 1. Cho nên là số 1 dùng bém rồi. Giờ chỉ còn mỗi số 0 dùng nữa thôi. So A and T are in thermal equilibrium. B and T are in thermal equilibrium. So then A and B are in thermal equilibrium. Very easy, right? Just like in math. Then, once we know the temperature, the zeroth law, we can go to the thermal expansion. So the thermal expansion is the tendency of matter to change its shape, its area, its volume, and density in response to a change in temperature. Okay, so we have the linear expansion and the volume expansion. For the linear expansion, here, this is just to remind you. I know for sure that you know it, you learned it. I remind you only here. For the linear expansion, what do we have? So we have the change, okay, in the length of a material will be equal to the product of the initial length and the coefficient of linear expansion and the change in the temperature. Okay, of course, for different material, we will have different coefficients of linear expansion. So we need to really pay attention on it for the real applications. For example, if we try to produce a bar, a metal bar, a brass and steel sticking together like this, we need to be very careful, because if there's a change of temperature, a decrease or an increase in the temperature, the bar might be bended, because they have, the brass and the steel have different coefficient of linear expansion. Then the change in the length will be also different. Similarly, we have the volume expansion, and the beta here is called the coefficient of volume expansion. Okay, very similar. Then the heat. I remind you the notion of heat. Heat is actually the energy transferred between a system and its environment because of a temperature difference that exists between them. Okay, in thermodynamics, heat can have a sign. It can have a positive sign or a negative sign. So you should pay attention on it. Yeah, this is an agreement in thermodynamics, a convention in a thermodynamics system. So, nhiệt có thể có dấu âm hoặc dấu dương theo quy ước, okay, trong một hệ thermodynamics. So, for example, here we have a system marked in green. Okay, marked in green, and we have the environment. These are outside of the system. We call it the environment or the surroundings. If the system has a higher temperature, so it will lose energy as heat. Okay, the system will lose heat. So this amount of heat, the amount of heat lost by the system, will take a negative sign. So Q is negative. Negative. If the system loses heat, this amount of heat will have a negative sign. Now, if the system gains energy as heat, then the amount of heat will have a positive sign. So you should pay really attention on the sign of the quantities in thermodynamics. So later on, when we study the first law of thermodynamics, you will see that the heat will also have a sign. The work will also have a sign, and the combination of them will make you have a headache. So in a lot of cases, you will make mistake if you do not remember very well the agreement, the convention of sign. When the system loses energy as heat, this heat will take a negative sign. When the system gains energy as heat, this heat will have a positive sign. Is it clear until here? I hope so. I hope
Yes.
so. I'm sorry, I made a mistake here. Stop sharing. I will share it again for you. Now, if you want to calculate the heat absorbed by a system or by an object, or loses or lost by a system or by an object, then we can use the formula, this one. Okay, so the heat equals the product of C delta T. What is C here? C is actually the heat capacity of an object, the heat capacity. Okay, so Q equals the big C delta T. If the whole object has a mass m, then in this case, we can rewrite the amount of heat absorbed or lost by the object. Q equal mc delta T. Q bằng mc delta T. So very famous here. The heat is measured in joule. M is measured in kilograms. T here, the temperature is measured in degrees Celsius or Kelvin. It's up to you, okay, or Fahrenheit. Then the C, you see the unit of C should have this unit. If you measure the temperature by Kelvin, it should be written in Kelvin, okay? If the mass is measured in gram, it should have the gram here. Why? So for the dimension from the left and the right to be similar, the dimension should be similar from the left to the side to the right of the equation. The dimension in Vietnamese we call thứ nguyên của bên trái này phải bằng bên phải này. Okay, the dimension. Yeah, and the small c here, we call it the specific heat of a unit of mass, of a unit mass of material of which the object is made. You may have other quantity that have the word specific associated with it. For example, you have specific volumes, specific entropy, specific enthalpy. So you know that when you have it, it should be something divided, yeah, to a unit of mass. Okay. And when we talk about the absorption of heat, there are some famous cases when the object changes its phase. The amount of energy required to change the state, but not the temperature, okay? When it changes the phase or the state, but not the temperature of a particular material of mass m, we can calculate using the formula Q equal Lm. Here, L is the heat of transformation. We can distinguish the heat of vaporization. This is when the material changes its phase or its state from the liquid to the gas. And inversely, when the material changes from the state of liquid to solid, or inversely, we have the heat of fusion. We have the heat of fusion. You can check the heat of vaporization or the heat of fusion on Google, okay? Each material will have a different value of heat of vaporization or heat of fusion. Even for ice and liquid water, these are not the same. For the ice, you will have a different heat of fusion. And for the liquid water, it will have a different heat of vaporization. Is it okay? Yeah, until here, I just remind you, nothing new for you, right? I hope so. Now let's try to do an exercise, a very small exercise. Here, if someone has the answer, so please share the screen for people. We try to do a little bit of practice here. If you have the answer, I will give you 5 minutes. If someone has
Teachers, I don't see your slide changes. We still in the slide of heat and absorption.
Okay. What happened to what happened? Do you see it right now? The exercise.
Yes.
That's it. So
Okay, so please do it in 5 minutes. Then, if you have the answer. So someone has the answer?
We don't have the C and the L of ice and water.
You can check it on the internet. You have to check the specific heat of water and of ice on internet. Please show the way you solve it, because I do not have the answer here. But for the question A, this is the way you are going to solve it. So the question A, how much heat must be absorbed by ice of mass m? Okay, we know the mass. That is equal to 720 grams at minus 10 degrees Celsius to take it to the liquid state at 15 degrees Celsius. So here, what we have to do, I'll try to write it down.
Can I answer it?
Yeah.
So I will calculate the Q total is by Q1 plus Q2 plus Q3, and the
What is Q1 to Q3?
Q1 is the amount of ice that is 0.72 multiplied by 2.2 and multiplied by 10.
I mean, the Q1 is actually the heat
of ice. Yeah.
to raise the ice from minus 10 degrees Celsius to 0 degrees Celsius, right?
Yes.
Yeah, very nice. So in this case, you will have to use the equation Q equal mc delta T with C, the specific heat of ice. Okay.
Yes. Yes.
So very nice. What is Q2?
M multiplied by LT, that is 0.72 multiplied by 333. Yeah.
So the Q2 is actually the heat needed for the ice at 0 degrees Celsius, turning to the liquid at 0 degrees Celsius. So just for the ice to melt, but not to raise the temperature. So then we can use the equation Q equal Lm, okay?
Yes.
With L, of ice. Then the Q3 will be the heat needed to raise
to 15 degrees state.
This time we have water.
Much.
0 degrees Celsius to 15 degrees Celsius. So once again, Q equal
MC delta T.
C delta T with C, the specific heat, this time of water. Okay, so you do the calculation yourself, but I think
yes. The total answer of the Q total is 300 kilograms.
Oh, really? Okay, so you verify by yourself. Okay, I do not do the calculation. How about the question B?
Yeah, I haven't do it yet, but I will do it now.
So then I will solve.
Can I do the question B?
Oh, of course, please. Very nice.
So first of all, I will minus. I will take 210 kilojoules the heat they give, and then I minus to the heat I need to raise the temperature of the ice, and then I take the heat which is left and I minus to the transformation heat.
Nice.
And because after that I got the answer is more, less than 0. So I think the final state of water is both solid and is solid because there is not the final state is both solid and liquid because there is not enough heat to transform all the water from solid to liquid, and the final temperature is 0.
Very nice. So your explanation is 100% correct. Okay, we just need to compare this amount of heat with the amount of heat needed to raise the temperature of this block of ice from minus 10 degrees Celsius to 0 degrees Celsius. And then once again, we compare it with the heat of transformation. Yeah. and the result is exactly what you said. So thank you so much. Very nice. I think we can continue. Sorry, I have to hide some windows because otherwise I cannot see my slides. Now, good. Now we go to the main and important part of this lecture when we talk about the first law of thermodynamics. Have you studied the first law of thermodynamics during the high school? Các bạn đã học
I don't
cái...
think so.
No, not yet. Okay, we are going to study now. I think you learned it already. Some of you learned it when I checked with people, maybe people from the gifted school or something, so they learned it already. Now, we have a question. How energy can be transferred as heat and work between a system and its environment? We are going to answer this question using the first law of thermodynamics. Firstly, we need to establish the first law. Okay, we need to establish it. Now, we have a system of a gas confined in a cylinder and piston. Here, this is our system. Okay. So a gas confined to a cylinder with a movable piston. Movable system. What do we have? The upward force on the piston is generated by the weight of the lead shot. Here we have a lot of lead shots. Okay. And the bottom rests on a reservoir for thermal energy. So the heat can be transferred from the reservoir to the gas or from the gas to the reservoir. Is it okay? And the wall of this piston, this cylinder, is very well insulated. Okay. And the gas does work on this piston. Does work. So here, actually, we have a closed system, remember? So we have no mass interaction, but we have energy interaction in the form of heat and work. Is it okay? Do you understand our system? Okay. Now, what do we do with this? We change the state of the system. I mean, here we consider the gas as a system, okay, of our gas from an initial state. Of course, we have PI, VI, TI, so the initial temperature, volume temperature, to a final state, PF, VF, TF. We change it. Here we perform a thermodynamic process. If you remember, we say that we perform a thermodynamic process. Then the energy as heat might be transferred into the system from the reservoir or vice versa. Remember, when the system receives the heat, so this amount of heat will have a positive sign. So the heat transferred into the system from the reservoir we have positive heat, right? When the system loses heat, then the heat will have a negative sign. Remember very well. The work is also the same. The work can be done by the system to raise the loaded piston. So we have positive work. Okay. We have positive work. And if the work is done on the system by the lead shots, so here I mean the piston is moving down, so we have an external force applying on the piston. We say that there's a work done on the system. Okay, and we have a negative work. So a work done by the system will be positive. A work done on the system will be negative. Please remember very well. A work done on the system will be negative. So this is our agreement. You can find in another textbook. They might have another agreement, but here we use the Holiday textbook. So this is our agreement, and we are going to stick with it from now on. Okay. If you do, for example, chemistry, they will have maybe a different agreement for the work to be done. Nếu mà các bạn học chemistry chẳng hạn thì có thể là các bạn sẽ có một cái quy ước ngược đấy cho cái công sinh ra bởi hệ đấy. Công tác dụng lên hệ thì là công âm, công sinh ra bởi hệ thì là công dương. Đấy là quy ước của cái chúng ta, của cái quyển Thermodynamics của Holiday. Nếu như mà các bạn học khóa chẳng hạn, một quyển sách nó khác thì nó sẽ quy ước ngược lại đó. Chú ý nhá. So we assume that all such changes occur very slowly. So the system is always in thermal equilibrium. Okay, always in thermal equilibrium. Now, let's consider if we remove a few lead shots. What will happen? In this case, the gas will push the piston upward, right, through a differential displacement with an upward force. Okay? When we say a differential displacement, we say that this is a very tiny displacement, We can assume that this force is constant during this tiny displacement. Then what do we have? We have F equal PA, with P the pressure of the gas and A the phase area of the piston. Okay, you learned the mechanics already, right? So the force is actually the pressure applied on a certain area. So then here we have F equal PA. No discussion until here, right? Easy. We try to be slow. Now, if you want to calculate the differential work done by the gas during this displacement, for a very tiny displacement, we have a very tiny work, right? We call it the differential work, dW. And actually the work is the product of the force and the distance traveled, right? So F ds. And if you rewrite the F equal PA here, and we develop the formula, we should go to the end. So the differential work in B equal to the product of the pressure and the differential volume, dV, okay? The dV is the differential change in the gas volume due to the piston movement. So dW equal P dV. Okay, is it clear? So I based only on the definition. The work is the force times the distance. This is mechanics, okay? And we rewrite the work. Okay, you can go out for the toilet and so on. Do not need to ask me. Just go back, okay? Let's continue. Once we have established the differential work as a function of PdV, then PdV, okay? Then we continue. If we remove enough the lead shot to allow the gas to change from the initial volume to the final volume, now we can calculate the total work done by this process. Actually, the total work is the integral of the differential work. Okay, remember the meaning of the integral. The integral is actually the sum of everything. Each time you remove a few lead shot, you have a different differential work. Okay, and then the total work will be the sum of every differential work. So you have the integral of dW, and you replace the differential work by the product that we just found, the PdV, and also the integral. You set the two limits from VI to VF. You would have this formula. Remember, this formula is always valid. It's always valid. So the work can be always calculated using this formula, this equation. Okay. Here it tells us that to evaluate the work, we need to know how pressure varies with volume for the actual process, by which the system changes from state I to state F. Okay. To know the work, we need to know how the pressure varies with the volume. Good. We can express this work using a PV diagram. We also call it a volume pressure loop. So the diagram is used to describe the corresponding changes in volume and pressure in a system. Here, as I said, each dot represents a state. We have the state 1, the initial state. We change it to state 2. And the work is actually the area below the curve. Okay, the area below the curve. We have the work done by the gas. We may have this curve, we may have this curve, we may have this curve. Remember, when we, for example, in the figure B, we have a process changing from 1 to 2 here with the V1 bigger than V2. then we will have a negative work. Here, it corresponds to a compression of the system of the gas, a compression. I mean, the system receives a force, an external force, right? So there's a work done on the system. That's why the work is negative. The work done on the system, not by the system, okay? Here, when there's an expansion, we know that the system does work, or there's a work done by the system. Then the work must be positive. Okay, let's go to more detail. We have the gas moves from I to F here, and the gas will do positive work, like I mentioned, because the gas expands. Okay, from I to F, we can find different way. If we go from I to A to F, we have a bigger work. We go like this, we have a much smaller work. So we say that we can control how much work it does to change from one state to another. We can control it. Here we enter to the case of a negative work. Negative work. Okay. Like I mentioned, a compression of the gas. We enter to a negative work. And here we have a loop. These are actually, you can separate it as two processes. So one process, you go from I to F. So you have W1 work, number one, okay? And then you go from F to I. You have a work number two. You see here, the W1, yeah, is bigger than the W2. And then when you say that the total work done by this system is actually the W1 plus W2, right? The total work. But here, the W2 will take a negative sign. Then it means the total work equal the W1 minus the W2. And we have the net work done like this. If we express it using the PV diagram. Is it clear until here? Crystal clear? I think we can do another stop. My throat a little bit hurt. So to sum up here, and then we take a break. A system can be taken from a given initial state to a given final state by an infinite number of processes, as you can see. The heat and work are path-dependent quantities. Okay, you see here. You see here. If we change the path, so I mean the process, then we will have a different work and also different heat. So we say that the heat and work are path-dependent quantities. Okay. However, experimentally, we found that the quantity Q minus W, so the heat minus the work, is the same for the all processes. This quantity is the same. Experimentally, we found this. So this quantity must represent a change in some intrinsic property of the system. Intrinsic property of the system. So we call it the internal energy. Okay, the internal energy. That's why we enter to the first law of thermodynamics. The first law of thermodynamics. This is the first law. So the change in the internal energy will be equal to the heat added to the system minus the work done by the system. The heat added to the system minus the work done by the system. Remember the signs, okay? The heat added to the system minus the work done by the system. If you change if you replace by the work done on the system, then the sign will be different. Remember, so the heat added to the system minus the work done by the system will give the internal energy of the system. And if you write it in a differential form, I mean a very tiny change. So we have the differential internal energy will be equal to differential heat minus the differential work. The first law tells that the internal energy of a system tends to increase if energy is added as heat, and tends to decrease if energy is lost as work done by the system. Okay, if the heat is added, so I mean we have a bigger Q here, then we will have a bigger delta E. Okay, and if we have a bigger W here, I mean the work done by the system is bigger, we will have a smaller internal energy WE delta E here. Is it clear? So we can stop here. We can stop here right now. Then we will go to the 4 special cases of the first law. Okay, we stop here for 10 minutes. This group, I go faster than the other group because for the other group, I lost a lot of time. I think it's better. We are totally on time. Continue. I got a question from Minh. Good question here. Please do not make any misunderstanding. Here, I say that Q minus W is the same for all processes having the same initial state and the final state. Okay, if by another process having another state, initial state or final state, of course, the internal energy should change. But if we have the same initial state and the same final state, no matter what processes you go, this process, or you use this process or this process, or whatever, or even this process, or this one, to go from I to F, the same I to the same F, no matter what processes you go, you take the Q minus W is still the same. I mean the change in the internal energy is the same, okay? It depends only on the initial and final state, not on the process. This is what I mean. Is it clear until here? So of course, for different initial state, different final state, we should have different change in internal energy. Okay. Same initial state to the same final state, you can follow different processes, but the change in the internal energy of the system is still the same. Is it clear, Minh? Lê Hoàng Nhật Minh?
Yes, I got it now.
Yeah, thank you. So if you have any questions, please do not hesitate to ask me. Let's continue here. This is the first law of thermodynamics. It is applied for all. Remember, the heat added to the system will be positive. The heat loss from the system is negative. The work done by the system is positive. The work done on the system is negative. Do not make mistake, otherwise you will find a different result. Yeah, for this equation. Tôi nhắc đi nhắc lại về cái dấu ấy. I repeat many times about the sign because last year students did a lot of mistake already. Vì năm ngoái là rất nhiều bạn đã bị nhầm dấu. Nhất là với những cái bạn nào mà chỉ cầm mỗi slide mà không nghe thì rất là nguy hiểm. Now we investigate 4 special cases of the first law of thermodynamics, and after that we can stop the class. The 4 special cases. Firstly, we have the constant volume process. Constant volume process. Or we also call isobaric process. Yeah. For this process, if the volume of the system is held constant, then that system can do no work, right? So please remember the work can be calculated as the integral of the product of pressure and differential volume. And if the volume is held constant, we have the work equals 0. No work done if the system does not change the volume, right? So in this case, we have the change in the internal energy will be equal to the heat added to the system. Then here, if the heat is absorbed by a system, or we say also the heat added to the system, then the internal energy will increase, right? And accordingly, if the heat is lost during the process, the internal energy will decrease. Is it clear? Totally clear, right? So this is the first case, the constant volume process. Remember, okay, if there's no change in the volume, the work of our system is always 0. Of our gas system is always 0. We are talking about the gas. Okay. For the adiabatic process, have you ever heard about the adiabatic?
No.
No. A process that occurs so rapidly or occurs in a system that is so well insulated that no transfer of energy as heat occurs. between the system and its environment. We call it an adiabatic process. In Vietnamese, đoạn nhiệt. Đoạn nhiệt. So no heat transfer. No heat transfer. I mean Q equals 0. For a process having Q equals 0, we call this process an adiabatic process. This corresponds to the case that the process occurs so rapidly, so no time for the heat to be transferred between the system and the environment. Or the system is so well insulated, so also no heat transfer. Then we have Q equals 0. In this case, the change in the internal energy will equal minus the work done by the system. So here, if the system receives work or there's a work done on the system, then the change in the internal energy will increase or decrease.
Can you repeat it again, please?
Now I say that if we have an adiabatic process, okay, and if the system receives a work in other words, there's a work done on the system, then the internal energy change will be positive or negative.
It will negative. It will decrease.
No.
It's positive.
Positive.
Receive.
Yeah. Positive. Why? For example, now if I add a work of 5 joule on the system, okay, 5 joule, then by agreement, this 5 joule will take a negative sign, right? Viết ngay là sẽ có bạn nhầm. Now, if work 5 joule is done on our system, okay? Then by agreement, what do we have? We have the work equal minus 5 joule. Because this is the work done on the system. The system receives work, okay? Then if we replace, here we have the delta E equal minus 5 joule. Okay, finally, we have an increase of 5 joule. So remember, okay, the work done on our system. There's a system on which the work is done. Okay, if a work of 5 joule is done by our system, I mean, for example, our system of a gas is expands so that it does work. And system does work. Hệ sinh công đấy, hệ nhận công thì là công âm, hệ sinh công thì là công dương. Các bạn hiểu chưa? Thế thì hệ nhận công thì trong tiếng Anh thì là work done on the system. Đúng chưa? Đó, và hệ sinh công thì work done by our system. Please remember very well. I try to explain it in both Vietnamese and English, so to be sure that you have no mistake, because this mistake is important. I try to delete this. I have to repeat many times because I still see that you have a confusion about the sign. Okay, if the work is done by the system, then the internal energy decreases by the amount of work. And if the work is done on the system, the internal energy increases by the amount of work. I'm sorry, by the amount of work. Chờ tớ chút, máy tính tớ đang bị đơ. I'm sorry, my laptop doesn't respond anymore. This is an old laptop. I bought it like 6 years ago. Yes, 6 years ago. It's still working, but yeah, a little bit slowly. Do you see my screen?
Yes.
Okay, thank you. So if you imagine, for you easier to imagine, for example, you have a certain amount of energy, right, of a system, and you take a part of it to do work. Yeah, to push something, to move something, then you will lose a certain amount of this energy. Để cho các bạn tưởng tượng, đúng không? Các bạn có một hệ mà các bạn có một cái số lượng, một cái số năng lượng nào đó. Nếu các bạn dùng nó để sinh công thì các bạn phải, nó phải tiêu hao đi chứ, năng lượng của hệ nó phải tiêu hao đi, đúng không? Đó, cho nên vì sao là sinh công thì cái change internal energy thì nó lại là giảm đi. Hệ nó sẽ mất cái nội năng của nó đi mà. Here now, a cyclical process we also call a closed cycle. You seen it already. This one, a closed cycle. Okay.
But you
yes, this one.
switch the slide.
Professor, we can't see the slide. Like it's still on the normal.
Actually, I fit already, but it doesn't work. So do you see my slide?
Okay.
Now we go to
Yes, we can.
cyclic process, a closed cycle. Maybe I need to find another laptop. I don't have money yet. Nghèo quá các bạn ạ.
Well, you could upgrade.
Yeah. I have a Dell, how to say, XPS Dell, and there's no way for me to upgrade it, I think, because the RAM is also stick with the main board. So if I want to really to upgrade it, I have to change the whole main board. I think it's not possible.
Does your laptop have an SSD or a hard drive? It could be the hard drive.
I have an SSD already.
Ah, okay. So that's the RAM issue.
Yeah, I think it's a RAM issue, but the RAM is stick with the main board. So I don't think there's an option for me to upgrade it anyway. 6 years already. I hope it will last for 1 more year, 2 more years, and then I change it. Okay, now let's go to the cyclical process. In a cyclical process, after certain interchanges of heat and work, the system is restored to its initial state. So here I mean the initial is also the final state. Okay, and if we remember, the delta E is actually the internal energy from the final state. I think here, I'm sorry, here I make a mistake. I will verify it. I make a mistake here. Actually, when we say the delta, the change, do you see my slide? No, maybe not yet.
No, we can't see it.
Yeah. Here, when we say the delta, the change, I didn't pay attention. When we say a delta, the change is actually the final, always the final one minus the initial one. Okay, change in volume, change in everything. It's actually the final state minus the initial state. Yeah, I did a mistake here. So let's go back. Yeah, so we have the final state is also the initial state. Then the change in the internal energy should be 0. We have a cyclical process. So in this case, the net work done during the process must exactly equal to the net amount of energy transferred as heat. So if the system receives heat, okay, or absorb heat, then the system will do work. So there's a work done by the system. If the system loses heat, then there's a work done on the system. Okay. And in a cyclical process, the store of internal energy of the system remains unchanged. Finally, we have a free expansion. So we have an adiabatic process in which there's no heat transfer, no work done. Okay, everything equals 0. Everything equals 0. Chán nhỉ, sao slide lại vẫn không ấy à?
Yeah, we can see just.
Chắc là bởi vì tới cuối máy nó nóng thôi. Okay, do you see the free expansion?
Yes.
Expansion. Actually, we have an adiabatic process. So Q equals 0, in which no heat transfer, no work done. Then everything equals 0. Q equal W equal internal energy equals 0. For example, I give you an example here. For example, I have this system. Okay, I have this system with 2 reservoirs. One reservoir from the left, we have the gas. One reservoir from the right, we have the vacuum. These 2 reservoirs are separated together by each other by a stopcock. This one. Okay, and the 2 reservoirs are very well insulated. So we have an adiabatic process. If we release the stopcock, what will happen? The gas here from the left will immediately take place, okay, of the vacuum of the reservoir from the right without exchanging any energy from outside because it's very uninsulated, and without doing any work. We do not need to do work because this is vacuum. We do not need to, the gas does not need to do work to push the air or something because this is vacuum. So it will go directly to the second reservoir without doing any work, without doing any heat transfer. So we enter to a case of free expansion. Okay, So we have seen the 4 special cases of the first law of thermodynamics. Here I summarize in this table, and you can just remember this table is enough for you to do a lot of things. These are everything for the first law. So the first law relates the change in the internal energy of a system with the change of heat and work done, the heat added to the system and the work done by the system. So this answer to the question how the energy change relates with the heat and the work, the question that we already raised from the beginning. And for the law, we may have several applications, the 4 cases of the first law. The adiabatic process, đoạn nhiệt. So the heat equals 0, okay, the heat equals 0. Consequently, we have the change in the internal energy equals minus the work done by the system. We have the constant volume. Then the work done by the change in the internal energy will be equal to the heat added to the system. Because for a constant volume, we have a work equals 0. We have a closed cycle. Okay, the initial state and the final state is actually the same. So we have the change in the internal energy equals 0. Consequently, we have the heat added to the system equals the work done by the system. And finally, we have the free expansion, everything equals 0. So I think this is done for us for today. Thank you so much. If you have any questions, please raise your hand. If not, let's go to have lunch. Or you can send me any questions by email, or we can also see each other once again in the tutorial classes. Okay. So if no questions, so thank you.
Teacher, I have a question. The previous slide, you have said that if the other side of the reservoir is vacuum, so we don't need work to push gas to the other side. So if in the reservoir that has vacuum, we replace by some kind of gas, but it has lower pressure than the other side. So does it have the work done by the system?
Lower pressure. So we have a change in the pressure anyway, right?
Yes.
Yeah. So that still work.
Oh, okay.
Okay. So any other questions? No? Okay, thank you so much. So I think we can stop now. We see each other, maybe some of you will be in my tutorial classes. Okay. So yeah, bye-bye.
Vâng, Professor.
Bye,
Bye, Professor.
Bye.